A warm welcome to everyone online. Welcome from here. I'm in Ottawa, Canada, where it's a balmy 5 degrees Celsius right now. So hopefully everybody's enjoying better weather than I am. I'm going to go through a brief overview of what we're going to be working on this week to sort of set the ground, make sure that everybody has an idea of where the various pieces fit and how it sort of all hangs together. So this is kind of like a introduction to the scenario. So I just sort of started with the premise of, okay, well, ultimately, for the end user, they just want to watch YouTube. Cellular data continues to explode. 5G is going to give us even more bandwidth. The backhaul costs for the cell providers is going to get more and more expensive. And the management of all of this software is expensive. To top it off, remote management is going to get even worse. Last thing you want to do is have what's called a truck roll. In other words, send somebody out to some sort of remote site to, fix things or reinstall or do any sort of repairs. So this week we're going to show how OSM helps with the management and orchestration of an evolved packet core, which is basically the overall set of processes that allow your cell phone to watch YouTube, as well as an over-the-top service to help reduce some of those backhaul costs. So here's a picture that some of you may be familiar with. If any of this is new, I'm going to hopefully give enough of a background on this that you get the idea of where we're going. But this is a rough outline of what a cellular data connection would look like. On the one side, you've got your cell phone. That's going to connect to a radio tower. There's going to be some type of networking that pulls it back to a regional data center. There's going to be some sort of caching, hopefully, in order to be able to reduce the costs of continually going out to the internet. And there's probably a firewall, a router that's preventing, any sort of intrusion from the internet back into that regional data center. So a lot of this is going to be existing in a real data center. I mean, this is a picture that exists today in various forms, but this is the reality of a lot of carriers today. You've got a whole bunch of parts that are sitting in here, and it's not all going to be shiny new software. Some of this is going to be, if you want to call it legacy, or if you just want to call it what exists today, or a brownfields environment, we still need to be able to work with all of that. So the reality is there's always going to be a state of transition. Even as Kubernetes takes over and becomes more popular and we're getting rid of physical appliances where possible, the next great shiny thing is serverless. And after that, there'll be something else. And there'll always be a new technology. And we're always going to be dealing with situations where there's going to be a mix of these technologies. So that's the reality. And the scenario that we're going to work through is actually going to show an integration of these different classes of network functions and how OSM can bring all of these together. So a conversion of what exists to where we want to go. So the software that we're using is Facebook Magma. This is going to provide us with the evolved packet core. It actually combines 3 different 3GPP functions into one function that they call the access gateway. So for those that are familiar with the 3GPP specs, we've got a mobility management entity. And as we dive in this week, you probably are going to be looking at some MME logs. And this is basically where the user equipment is registered. You can see devices coming online. You can see radios coming online there. And it handles the request for network access, setting up, tearing down data sessions between the cell phone and the packet gateway. So then you've got a serving gateway and a packet gateway. Oftentimes these two are combined into one function, but the 3GP spec actually has them as separate functions. So the serving gateway is technically responsible for handling the signaling between the MME and the packet gateway. And lastly, the packet gateway is what actually, it's the termination of the tunnel that is set up between the cell phone and the internal operations, the internal functions inside the data center, and it then breaks you out and puts you out onto the internet. Often there'll be natting and whatnot going in here, so there's a lot of complexity about the routing that would happen. But we'll actually be talking about some of the routing that might need to happen as we go on later through other sessions. Now for a little bit something different. We're not actually going to give you all cell phones, and we're not giving you all radios. We're actually building this up in software. So there is open source software that allows us to emulate the user equipment as well as the eNodeB or the evolved NodeB, which is the radio. So some of the things that we're going to be diving into, we're going to be pretending to use a cell phone, but we're going to use actual software that's built inside a VM that will do this for us. So the signaling from the cell phone towards the radio and the signaling from the radio towards the MME, all of that is going to be real 3GPP traffic. So Magma will think that it's talking to a real radio. So going back to this picture, how's it look? How are we going to build it up? Well, the first thing we're going to do is we're going to be calling up OSM. OSM has been introduced to this picture, and I'm showing it here in a central data center. The reason being is that we could have one and only one OSM that speaks to multiple data centers scattered throughout the world, throughout a region, throughout a continent, whatever the reality of your infrastructure happens to be. You do not need to have an OSM in each location. It is capable of going over a layer 3 network, routing, and providing these operations regardless of where your data center and the operations need to occur. So the first thing we're going to do is we're going to be taking this packet gateway, this rack of servers, and the web cache, and we're going to be converting them to virtual functions by first creating or setting up a virtual infrastructure manager, in this case OpenStack, and a Kubernetes K8s cluster to consume Docker images and be managed through Kubernetes. From there, we're going to be deploying the Magma orchestrator, which is a series of KNFs or Kubernetes network functions. This provides all of the management infrastructure for Magma. It is, if you will, the control and management of Magma. It is not involved in the data plane at all. No cellular traffic will be going through this. This is the element management system for Magma. Next, we're deploying the Magma vEPC, although I should actually call that the A gateway because that's what I referred to it as earlier. But the Magma vEPC is going to be deployed as a VM. From there, we're also going to be deploying our generic eNodeB and user equipment emulator. This was the software for the radio that I talked about earlier. We're not actually going to be deploying a virtual router. For our environment, we are pretending that our firewall, our physical router, exists, and our security group said, you're not going to upgrade that. You've got to use the one that we have in place because we trust it. So now I have a constraint. I have to talk to an older system, something that's been locked down, and something that doesn't necessarily have any sort of management or orchestration. Sorry, it has management, but it doesn't have an orchestration engine in it. And lastly, we've got a web cache that we're going to be deploying. This will be a straight up Kubernetes container from packaged using Squid. If anybody's familiar with web caches, Squid has been around for a very long time. It's quite mature, and it was a relatively simple thing to put into this picture. Again, the purpose of actually having a web cache here is to reduce the costs of going out to the internet by caching content within a regional data center. Other over-the-top services can be added here. It doesn't necessarily always have to be a web cache. We could have things like a content distribution network, or CDN, where, say, for example, we want to replicate some of YouTube directly from YouTube and not rely on caching to do that, but actually have a push mechanism from YouTube or Facebook or whatever content we want to have distributed. That could actually happen inside of a data center to reduce costs as well. So what does this look like? I mentioned that over here on the left, we've got our racks. We've got this mix. We've got these physical network functions on the left, which is our router, our firewall, which we're not allowed to upgrade and convert to a VNF. We have to use it in place. We have to use it as is. We've got some virtualized VMs, network functions, that are going to be running and executing on our VIM. And over on the right, we have Dockerized network functions that are going to be running on top of Kubernetes. So with all of this, we have orchestration code, operational code that needs to run. And that operational code will need a place to live. So some of these, like for example, the physical network functions, we're not putting operational code in there. We're going to need to have it hosted remotely through what's called a proxy charm. That's our operational code, and we're carving out a space for it to execute within the OSM environment. So this code doesn't exist and doesn't touch the PNF. PNF, as far as it knows, is perfectly happy and has no new software, doesn't know that there's something new that's talking to it. So OSM carves out this space, creates this environment for the operational code to execute, this proxy charm, and that will then reach out to the PNF and perform operations. So we can have state and sequences of events, relationships, and management of sort of what happens next in the order of operations managed inside of here, as well as OSM. So now we have a path where our network function hasn't been touched, but we've got operational control and we've got code. The next thing is we can do that for VNFs as well. In the case where the VNF has already been developed and deployed, and we don't want to put new software inside of it or touch it necessarily, we can do that here too. Now, the next fun part is we don't always have to have this proxy. We can actually have the operational code built inside with the VNF and skip this step and have these things execute directly. So at this point, the operational code and the native charm is side by side with the application, and it can run in that same space. The same is true for Kubernetes side. We can have native charms that work right alongside the Kubernetes functions or run through a proxy charm. These are some of the, we're actually going to be breaking down some of these examples, actually each one of these examples later on throughout the week. So as you have, this is laying the ground of what we're going to be doing, and we'll give you opportunity to definitely ask a lot more questions about this as we progress. So this orchestration, this operational code, what exactly is it? It's last mile specific workflows. They're scripts. They're property file changes or any file changes, configuration changes, integration, backups, restores even. They're separated into what's called day one and day two type operations. Day one being something that you would do, when the software is first deployed. It's sort of an initial configuration, and day two would be the type of thing that would be repeatable on an ongoing basis. For example, in my Evolve Packet Core, every day I'm going to be getting new subscribers, and the reality is I'm going to be losing some subscribers. I'm going to have to deactivate them and unregister them from the network. So those are the day two type operations, whereas the initial configuration of the packet core is a day one configuration. So these are the scripts that are packaged in what we called earlier, what the name is charms. So they can either be proxy, where it acts on the network function from a distance over a network protocol, SSH, REST, netconf, etc., or native, where it's running right inside with the function. So that can be installed on Windows, Ubuntu, Red Hat, etc., and it could be a Docker image that can be driven directly by the charm. And somewhat importantly, there's no need for an open management port. So you can actually reduce your attack surface from a security perspective by not needing to have an open port for SSH or REST. So there are some advantages to having the charm run natively that go beyond just ease of coding. So coming back to our picture, here's the cellular data path that we were showing earlier, and this is how we are going to be demonstrating the orchestration as we go through this week. Physical router, obviously, got to be a proxy charm. Native charms will run on our KNF and our eNodeB simulator, and proxy charm for the Magma vEPC as well. So what is a charm? It's a package of scripts that are used to drive applications. So there's life cycle scripts like installation and configuration, updating, removing, scaling in, scaling out. And there's sort of integration type scripts where you can form relations between two or more of your components. For example, I happen to have an application that starts up. There's an application and there's a database. And the application needs credentials for the database, and the database needs to have a table for the application. So there's a relationship dependency between these two things. Somebody's got to generate the credentials and make sure that both sides are aware of how to log into the database. Okay, I'm just doing a quick time check here to make sure that we're on time. The Magma vEPC is a combination, as I mentioned earlier, of Kubernetes and virtual machines. So this example has chosen Magma as the vEPC. There's the URL for it. These slides, as Sylvia mentioned, are available as well on the OSM FTP site. So it's a clickable link that you can go and get at any time, get more information about Magma if you desire. So the management, as I mentioned, is a series of Kubernetes containers, and the access gateway is a VM. So the VM can be configured to use SIROV, CPU pinning, huge pages, etc. Later on this week, we're going to be getting into a session where we're going to be talking about the orchestration of guest awareness, so that there are things like SRIOV that can be managed by OSM. So some of these enhanced services This is not just, oh, I need to go into OpenStack and manually configure it. OSM does take care of a lot of this for you. Something else that I'll mention as well, there's a new technology that's being introduced in OSM, which is referred to as placement. And we'll be talking about that a little bit later as well, where decisions can be made as to where certain virtual units will be placed based upon a cost analysis. So the Magma Access Gateway is going to need to have some information. When it registers itself with the Magma orchestrator, it has to have an ID and a name. It also needs to know where that Magma orchestrator is, and it's going to be creating a name for itself, a network name for itself inside of the Magma orchestrator. This is easy information that we're going to be giving into it, into the orchestration engine, and we're going to be demonstrating this using proxy orchestration charm. The PNF router, well, this is a straight VIAS router. It's not customized. There's nothing that we have done to it. It's locked down. There's no software to deploy. However, simple, it's got to be registered with OSM for orchestration. So we're going to be creating a simple, placeholder or a registration of the physical network function that represents the router so that OSM knows how to get to it and how to talk to it. And then we'll be configuring routing to permit or deny traffic from the access gateway out to the internet, or from the web proxy out to the internet, depending upon which path we're demonstrating at that time. So this is, again, going to be demonstrated using proxy charms. Next are eNodeB and user equipment emulators. We're simply going to be deploying a VM with the SRS LTE project. Again, there's a URL if anybody needs more information about that or wants to dive into it further. But basically, this is just going to be like a VM, and it's got a graphical desktop with Firefox on it to sort of make a placeholder for what it would look like to pick up your phone and launch a web browser on your phone. The configuration for the eNodeB+UE is, well, where is my EPC core? That would be for the radio side. The radio needs to know how to attach itself to the EPC core. So there's some radio parameters, which is basically kind of your country code, your locality code, and then the user equipment parameters, the IMSI and encryption keys. These would be things that would be burned into your SIM card that you would receive from your provider. So we're not actually going to be passing in these encryption keys. We're going to act as if they were hard-coded, just like they would be on the SIM card. And the bringing up of the radio and attaching it to the network, as well as starting the cell phone and attaching it to the radio, will be demonstrated using native orchestration charms. The web cache. So OSM is going to create the container based on Squid. We're going to demonstrate this with a native Kubernetes orchestration charm, and we're going to be adding and removing URLs from a whitelist. So Squid by default is set to a lockdown mode, which basically says, it doesn't matter where you're trying to go or what web page you're trying to hit, we're going to give you access denied. And you're going to need to use a day 2 configuration of OSM to add new URLs to the whitelist and allow traffic to pass through it. So going back to our big picture, here's our EPC, here's our UE and radio, here's our physical router, and here's our Squid KNF. These interfaces are networks that will be created by OSM. And for those that are familiar with 3GPP specs, these SGI and S1 have specific meaning as far as what the traffic is. The S1 being signaling from the radio towards the packet gateway, and the SGI being the traffic that comes out of the encrypted tunnel between the two of these and heads towards the internet. One concept that we're going to introduce here, and that we'll be using a couple times during this week, is the concept of a network slice. One of the things that we're going to be doing is we're going to be launching this slice. And what it will do is it will bundle together the Magma orchestrator, the management, the EPC, and the radio, excuse me, and the radio. Even though these are individual units, we're going to be deploying them and treating them as a unit. So this is something when we get into the network slicing that can be explained in more detail. But it's introducing it here so that you're aware that OSM doesn't have to treat everything individually, and that multiple units can be pulled together in one network slice. So lastly, our cell phone. It's the VM that has the software. It's really an Ubuntu desktop. We're using it as if it is a cell phone. We've got two ways of being able to access the desktop. If anybody's got VNC, you can VNC directly to it. Or if for whatever reason VNC is not working, it's not available, you don't have it installed, you don't want to play around with that, we can go to the OpenStack Horizon dashboard, which would be for this URL is the same. You'll get the username and password to log into later today. But that will be the URL that you go to, and once you get the desktop, you would log in with the username Ubuntu and password OSM 2020. Yeah, so I mentioned this before. The SIM card would have credentials built in, and that would need to be activated in the EPC. So we're going to be showing a day one primitive that creates this registration in Magma automatically. And then we've got some day two primitives to start and stop the radio. There are other day two primitives that we'll be demonstrating, but this is kind of the basic of the core. There we go, end to end. We've got all of our pictures that are going together. We've got our traffic flow right from the radio, from the cell phone out to the internet. And over the next 3 days, we're going to be breaking this down step by step, teaching you how this is done, teaching you how to do it for yourself so you want to, and showing you how each part got created. So hopefully you'll enjoy this week, and thank you very much. I believe we're ready to hand it off to the next session. Are there any questions, first of all? The software that emulates the user equipment is, I'll go back to it here. Right here, SRS LTE. So this is an open source project that is actually a full EPC emulator and software. They have the SRS user equipment, the SRS eNodeB, and the SRS EPC. Each one of these pieces can be used independently or in conjunction with each other, as well as can be combined with real radios or real handsets. So there are people who have used the SRS user equipment with a real radio, the user equipment emulator with a real radio, to test out some functionality. And I'm sorry, I'm seeing there are questions coming in, but for some reason, GoToMeeting is not letting me see my messages. I may have missed some. So I believe there was a question about certificates with SQUID. And the short answer is we are not, sorry, SSL with SQUID. The short answer is we are not addressing that as part of this. We're using SQUID, when it comes to SSL, we will be using SQUID for the whitelist, blacklist only. So it will only allow or forbid URLs, but we're not getting into the whole man in the middle issues that surround web caches and SSL certificates. It's just a little too complicated. I'm sorry, if there are more questions, they might need to be re-asked. I honestly don't know where my GoToMeeting chat window has gone. In our demo, the eNodeB and the cell phone are all in software. There is no real hardware in today's session for radios. Internet connect between eNodeB and user equipment is actually in memory in this case here because we're running the SRS software. So it is going to be using a what's called the 0MQ driver. So it is a message queue driver that goes over Ethernet. Yes, it is possible for this entire setup to work on a single machine. And lastly, where can we get the slides? I believe at the end of all of this, Sylvia, as part of our wrap-up, will be able to tell everybody. There is an FTP site with all the slides on it, but I don't have it handy at this exact moment. Is there any calculation about CPU and memory requirements in terms of users to be served with this approach? No, we have not done any scale testing. We have not done any sort of load performance on this. This is a Hackfest demo only and must be treated with that in mind. Especially, if you're going to be taking this and running this in your own environment, there's no guarantees that it will work beyond 1 or 2 users, perhaps. However, be noted that the set of servers that we're using today, we have 50, 60 participants with VPN connections, and each and every one of you is going to be creating your own Magma and your own radio and your own cell phone, and you're each individually going to be passing traffic through all of that. So here's an example of a bit of scale. Is there a DB acting as HSS? Yes, that is part of the Magma orchestrator. So the enrollment and registration of users is done in the Magma orchestrator in the management interfaces of Magma. As far as is it a proper HSS and does it fulfill all of the HSS functions? I actually have not looked into Magma deeply enough to know if it does all of the S6A protocol or if that's handled internally to Magma.